You're welcome to the GMAT 41 Elementary Mathematics class. In our class today, we are introducing the topic surds. You will recall that in previous class we treated quadratic equation. In this class, we shall look at certain numbers that are irrational numbers. Surd is one of them. But before we move on into talking about surds as irrational numbers, I'd like to ask you a question. Have you heard of rational numbers before? Rational numbers are numbers whose decimal has exact values. So we could have either terminating decimals or recurring decimals. These type of numbers, they fall under rational numbers. Quickly as an example, if you evaluate 1 over 2, you're going to get 0.5. So we know that's the exact value. 0.5, it terminates there, it stops there. What about values like 1 over 4, you get 0.25, it terminated at a point. So such fractions are known as terminating decimals, and they fall under rational numbers. Okay, think about this one. 1 over 9, if you evaluate it, you get 0.11111, and the 1 continues. Now, we don't know where the 1 stopped, but we know that the number continued with 111. Such numbers are known as recurring decimals. Alright, they fall under rational numbers as well too. There is this type of fraction also. If you evaluate it, you would get a certain order of arrangement. Maybe after the first 3 digits, the 3 digits will still repeat again and continue repeating. Are you following? Those decimals also fall under rational numbers. Now, let us bring our mind back now to surds, which fall under irrational numbers. What are these numbers? Numbers that your decimal is not exact. Numbers that do not produce terminating decimals. Numbers that do not produce recurring decimals. Example of such number is the value of pi. The value of pi, alright, the decimal, if you look at it, there is no defined order for it. What about the value of natural logarithm exponential? It doesn't have a defined decimal arrangement. These numbers are irrational numbers. And good enough, surd is also one of our irrational numbers. So we have on the board here that surds are irrational numbers. Okay, and they are written as square root of non-perfect square numbers. What do we mean by non-perfect square numbers? To understand that, you want to first remember that we have perfect squares. Perfect square number are numbers. If you find their square roots, you will get a whole number as a result. For example, 1, the square root of 1 will produce 1. It's a whole number. The square root of 4 will give you 2. The square root of 9 will give you 3. The square root of 16 will give you 4. The square root of 25 will give you what? 5. These numbers are perfect square numbers. Okay, 1, 4, 9, 16, 25, 36. They are perfect square numbers. Now, there are these numbers that if you find their square roots, okay, they won't give you a whole number. These numbers, when covered by square root, refer to them as surd. For example, root 2, that is square root of 2, square root of 3, square root of 5, square root of 7, okay, square root of 11, they are all Surdic numbers, because if you evaluate the square root of these numbers, you will get decimals. Decimals that are not terminating, decimals that are not recurring. Is that okay? So these numbers 2, 3, 5, 7, 11, they are non-perfect square numbers. And their square roots are classified under surds, which we also refer to as what? Irrational numbers. To start with, we want to consider the laws of surds. Is that okay? The laws of surds. First, we want to look at multiplication and division law of surds. Quickly, let us consider this. If you have root AB, for simplicity, square root of this AB, we'll pronounce it as root AB. This is root A times B, okay? By multiplication law of surds is equal to root A times root B. Does that make sense? Which simply tells us that square roots, or simply roots, distribute over multiplication. Is that okay? As a good example, we have root 15. Root 15, you see there, is the same as root 3 times 5 like this. And because root distributes over multiplication, we can actually expand it out like this. So you have root 3 times what? Root 5. Take note of that. Let us now consider division law of surd. If you have root A over B, alright, this root sign is covering this fraction. It's equal to root of the numerator A all over root of the denominator B. Once again, this tells us that square root distributes over what? Division. That is why you could split it. Is that okay? As an example, root 2 over 3. So the fraction here is 2 over 3 is equal to root of the numerator 2 divided by root of the denominator 3. Now, let us consider addition and subtraction of surds, okay? Because there's something very important we should know there. We have this short note to guide us that surds can only be added or subtracted if and only if their Surdic parts or their Surdic numbers are the same. So you see there is a conditional statement that if you violate this condition, it means you cannot add, you cannot subtract the Surdic numbers, alright? So you can only add or subtract surd if their Surdic numbers are what? The same. Look at, as an example, we now want to consider this. We would add this as law number 3 to this. This third law comprises both of addition and subtraction together. So when do you add or subtract surd? That happens if their Surdic numbers are what? The same. You can say this, x roots a plus or minus y roots a. No matter what is multiplying the roots, as long as their Surdic parts are equal, and you see that root A, you can add or subtract them. How do we solve that? It's equal to simply factorize the common root A. Look at it. Then add the numbers multiplying them or subtract the numbers multiplying the roots. So we have x plus or minus y, then times the common root A. As an example, 2 root 3 minus root 3. Take note that this minus root 3 is the same as minus an invisible 1 times root 3. Are you following? Now, their Surdic parts are the same. That is root 3. So you simply factorize it out. Then we'll have 2 minus the invisible 1 here. Look at that. And 2 minus 1 will give us 1. 1 times root 3, we have root 3. Look at another example here. 5 root 2 plus 3 root 2. Take note that their Surdic parts are also equal in this case. So irrespective of the number multiplying the Surdic part, as long as this Surdic part is the same, you factorize the Surdic number, which is root 2. Then we can add up 5 and 3. You have this, which gives us 8 root 3. So this is how we do addition and subtraction of sorts. Their Surdic numbers must be equal, must be the same for you to be able to add or subtract. Otherwise, you cannot add or subtract them. Please take note of this. Don't do this, okay? It's not allowed. If you have root A plus root B, take note the Surdic numbers are not the same. So you cannot, it's not equal to root then A plus B, saying that, okay, you're covering the A and B with all the square roots. You don't do that under addition. Please, square root does not distribute over addition. The same way it does not distribute over subtraction. So you can't say root A minus root B is equal to root A minus B. No, it's not done. That's why we put the sign not equal to. Is that okay? So what happens to multiplication and division here does not apply to addition and subtraction. The reason you see their Surdic parts are not the same. In the next video, we're going to look at how we can rationalize sort. In the case where we have divisional relationship and the denominator bears a Surdic number. In this video now, I want to look at sort rationalization. When is it necessary for us to rationalize sort? And then how do we rationalize it? So that's what we want to consider here. First, we rationalize sort once we see a Surdic number in the denominator of a given problem. Once you see the denominator roots something, alright, so you need to rationalize. Is that okay? Good. How do we now rationalize? We've got two methods we are going to apply here. Alright, we have the general method where we apply the conjugate of the denominator principle. Is that okay? And then we're going to also talk about the Omaker's UDRL multiplication method. The UDRL then means up and down, right and left multiplication method. Of course, that's how we go about obtaining this formula that we use in solving sort rationalization. Quickly, let's go through this general method. Is that okay? Let's go through that. For you to apply this general method, then you must know the conjugate of any denominator given to you. And that's why I've tried to bring out 13 possible denominators and their conjugates. The first one we have is x root a. Remember, this x and a here, they are numbers. Y's, they're all numbers. So x root a, its conjugate, good enough, happens to be the same x root a. That's the simplest form. Then we now have the next one, y plus x root a. What's the conjugate? All we need to do is to change the sign of one of these two terms. Either you change the sign of y, then maintain the sign of x root a, or you change the sign of x root a and then maintain the sign of y. That's why look at this, we have y, I maintain the sign, and then came to this plus and change it to minus. So x root a. Or you can do minus, change the sign of y, then maintain plus x root a. Take note that this plus could also be minus. If it is minus from here, then taking the conjugate like as in this case, this minus become what? Plus. That is if you maintain the sign of y. And if this is minus, then here, changing that of x root a to become plus here. Is that okay? Alright, now the next one we have x root a plus y root b. So if you have x root a plus y root b, what's going to be the conjugate? The same thing, change the sign of one of them. So in the first case, I chose to say, okay, I maintain x root a, then change the sign of y root b. And you can see that it becomes minus here. Or you maintain the sign of y root b, look at it, plus y root b, then change the sign of x root a, which becomes what? Minus x root a. So once you get this conjugate, the next thing to do is to multiply the numerator and denominator of the given Surdic fraction by these conjugates, and then start simplifying. You'll surely get the result. We now consider the Omaker's up and down, right and left multiplication method. Okay, so this is it. Okay, it's a formula, so it's expected that you memorize it. But let me show you how it actually came about. Just imagine that we have a and then plus b root c. You have to go in this pattern. I'm going to show you, please. Remember, it's a principle, and so you need to follow it. Okay, so that you don't get into trouble. So this is how we go. The up and down multiplication, the first direction is a times d, up and down. So we have a times d, that's the first multiplication direction, and that's going to give us 8d. Then minus, you come to this 10, another up and down multiplication, which is b root c times e root f. b times e, and then times root c times root f. Look at that. This is the second direction of multiplication, and that is going to give us b times e is be, then root c times root f. Using multiplication law of sort will give us root cf. So get be root cf. You can see that here, right? So once you are done with the up and down multiplication, enclose it in bracket, put plus. Then move to right and left multiplication direction. And in the right and left, what do? Watch. You go this way, this is your right. So from there, you come down this way, and then your left, you come down this way. Remember, from up, down. Is that okay? So you go right up and then down. Right, left, and then down. So that's the principle. Remember, like I stated, you are expected to follow the principle if you want to use this method. Good enough. This method is faster to obtain results than using this method. Okay, that is the Omaker's UDRL method. It's faster than using the conjugate of denominator method. Okay, now let us go. The next we stated that the third direction of multiplying is this. And then if you multiply b root c with this d, you're going to get b times d, which is bd, and then root c. Then put your minus, and then go your last multiplication, which is left to this way. There is the fourth direction of multiplying. Is that okay? If you multiply a times e root f, you get a e root f. Look at it. Does that make sense? Then all over, the denominator is a simple one. Square this term, square this other term, then put minus between them. If you take the square of e root f, you're going to get e squared, which is this, then square of root f. That square would remove this square root. So that is the Marcus UDRL multiplication method of surd rationalization. In the next video, we shall pick questions, and then we should apply all the laws that we've written so far about surd. In this video, let us solve this question based on surd simplification. We are required to simplify root 45 and root 200. Of course, this is a single surd. A single surd. Now, given to us, it's expected that we break this thing down, alright? We should break it down and, of course, get it in a form that is no longer single as this, as much as possible. Okay, now, let us see how we handle this problem. The first is root 45. Please, take note of these. The first thing you have to do whenever you're given a single surd is to find a way you can break it down into getting a perfect square from the number there, if possible. You need the knowledge of multiplication table absolutely here. For example, in the case of 45, 45 contains one perfect square number, which is 9. If you go to 9 times table, you will take note that 9 times 5 is going to give us 45, and 9 is the perfect square. So we're going to write this as square root of 9 times 5. Square root of 9 times 5. Alright, now we see that there is multiplication here, so what do we do? Quickly, we'll break this thing down to square root of 9 times square root of 5. You recall multiplication law of surd, that surd distributes over multiplication, so we can split this square root sign over these two numbers, getting square root of 9 and square root of 5. Simply pronounced as root 9 times root 5. Okay, let's go. 9 is a perfect square number, so the square root is 3. This is going to give us 3 times root 5. 5 is not a perfect square, so it's a solid number. We'll leave it in that form. Therefore, root 45 is simply equal to 3 root 5. And that is the result of this. So we can use that same principle to solve the second question quickly. That's root 200. And you notice that 200 can be broken down into root 100 times 2, which of course will give us root 100 times root 2, applying multiplication law of surd. This will give us to be root 100. 100 is a perfect square. And so we're going to get 10 from there to find square root of 100. So 10 times root 2. What does that tell us? Therefore, root 200, our result is equal to 10 root 2. So you see we've obtained our results in terms of mixed surd from this single surd. Right now in the next video, we're going to see a question where it will be required that we change this mixed surd back to the single surds. We now have the second question here to solve, okay? These questions on the board, these are mixed surd, and it's required that we express them as single surds. Alright, the work here is simply to change these mixed surds into single surds. Now, I've tried to bring back the answers we got for question number 1, alright? Because what we're now expected to do is working back the answer to get the question back as to what we saw in question number 1. So I've decided to bring out their answer so we can solve it, reverse the process, and see if we get the questions that we solved in question 1. So please, at the end of solving this question, compare it with question 1 and see that we obtained the question that was given to us there. Because that question 1 we're given single surd, and then we solved and got it as a mixed surd. So this time around we are reversing the process. Is that okay? So what do we do in order to express a mixed surd into a single surd? It's a simple process, alright? Now you're taking of this, take the square of the term given to you and then cover it with square root. This is a mathematical process that does not change anything, because if you take square and square root of something at the same time, you've not really done anything to that thing. Is that okay? So let's see how it goes. The first question we have 3 root 5. So like I said, take square of the term and enclose with square root. Square root. So that's the mathematical procedure we're going to apply. Is that okay? So we go. This is 3 root 5. It's not going to be 3 root 5. We are going to square this term. You see this, right? Then after squaring, you have to enclose with what? Square root. So I'll put in square root like this. Mathematically, I've not committed any error. Because you see, this square root can still remove this square from there, following power law of indices, you know? Because this square root simply means raised to power 1/2. So I'm still mathematically consistent, accurate. Is that okay? I've not changed the question given me. Okay, now having done this, what will I do? I will distribute this power 2 to this term here. Distributing this is going to give me square root 3 square and then root 5 square. Are you saying this right? I've allowed this square to affect this. This is power. That power distributes over multiplication. So this is still correct. And then this is going to produce square root of 3 square is 9, then times square of this square root of 5. This square will remove this square root. Is that okay? And then you'll be left with 5. Therefore, 3 root 5 as a single surd is simply equal to 45. Now, if you take your mind back to question number 1, you notice that it was root 45 that we solved to get 3 root 5. So this is just a procedure. It's a simple one. Take square root of the term and enclose with square root. So let us quickly apply that principle to the second question. We should be expecting to get root 200 because that's actually what we solved as a single surd to get 10 root 2. So we apply the process. This is simply 10 root 2. We're going to square it and enclose with square root. So 10 root 2 now is equivalent to square root. Distributes this power to this 10 and root 2. So we're going to get something like this. Fine. So this square root of 10 is going to give us 100. So I have 100 times square of the square root of 2. This square will remove this square root, so you're left with 2. Therefore, 10 root 2 is simply root 200 as a single surd. So that's that. We now want to consider the third question. On the sort here, we have to evaluate root 18 plus root 3. Then the second question, 3 root 50 minus 5 root 32 plus root 128. This is based on addition and subtraction of surds. And of course, we need to apply the knowledge of addition and subtraction of surds. When we introduced the laws of surd, we stated that surds can only be added or subtracted if their surdic parts are equal. So that's the knowledge we're going to apply here. Please, at the end of my solving this question, as you follow along what I'm going to do, apply similar principle, test your zone of proximal development by evaluating this. 3 root 50 minus 5 root 32 plus 4 root 8 minus open bracket root 2 plus root 1800. Do not be intimidated by how long the question is. Just use the same format, the same procedure, the same explanation I'm going to give to solving these two questions. And you'll see your results appearing there. Is that clear? Okay, now let's do this. The first part of the question is root 18 plus root 3. Okay? Now what we're going to do is to see how we will break down this number. Root 3 already is in its smallest form, its least form, because we've gotten the prime number there. 3 is a prime number. It's not a perfect square, so you can't break it down any further. This 18, we'll find a way to see how we can break it down to get possibly a prime number from it and a perfect square from it. And of course we can do that. 9 times 2 will give us 18, is that so? And 9 is a perfect square, why 2 is a prime number in that case. Although 2 is also an even number. Okay, now let's go. This is going to give us root 9 times 2 and then plus root 3. Then applying multiplication law of surd to this 9 times 2, you know that this square root can distribute over 9 and this 2 because of this multiplication. Roots distribute over multiplication. So we can split that down. You can actually work that out with the network of your brain. We don't necessarily need to write it down. Root 9 will give us 3 because 9 is a perfect square. Then times root 2. 2 is not a perfect square, so we maintain it like that. 3 root 2, that's the value of root 18. Then we're going to add root 3 to it. Alright, can we add these terms? The answer is no. The surdic parts, root 2, root 3, they are not the same. Suppose this were to be root 3, then we can add this up to get 4 root 3. Or suppose this were to be root 2, of course this is also root 2 here, the surdic part will be the same, then you can add up to get 4 root 2 because this becomes 3 plus the invisible one you're giving us 4. But you cannot add this because the surdic parts are not the same. And there's no way we can break this down again. Therefore, this becomes our result. We cannot break this any further down because this has reached its lowest term. This has reached its lowest term. These are surds, proper surds now. Okay, they are not perfect squares, so nothing can be done to them. Now let's look at the second part of the question. Alright, that is 3 root 50, and then we have minus 5 root 32 plus root 128. Once again, apply that knowledge, that principle that we need to break this down and see if we can get the same surdic part in each of the terms there. We have 3 terms here, 1, 2, and 3. So let us start thinking of how to break this down. Like I told you earlier from the first question we solved, we need the knowledge of multiplication in doing this. I said that in the very first question number 1 we solved on the surd. So with that knowledge, we're going to work in this. This is equal to 3 root 50 is the same as 25 times 2. That is root 25 times 2. Because 25 times 2 gives us 50. Now we've been able to break down this 50 to a perfect square number 25 and a prime number 2. Is that okay? Then minus 5 times 32 can be broken down to 16 times 2. We know that. Once again, we've been able to break this down to a perfect square and a prime number. Then coming to 128, we can break this down. This will be 64 times 2. 64 is the perfect square there, perfect square number, and then 2 is the prime number. And we can actually apply the multiplication law of Surdic to each of the root parts. Is that okay? So let's do that. We're going to get root 25. 25 is the perfect square, so it will produce 5 for us. Square root of 25 will give us 5. So that 5 will come out of the square root sign. Is that okay? It will come and multiply this 3 here. So we're going to have 3 times 5. This 5 came out from square root of 25. Then we have times square root of 2. 2 is not a perfect square, so it will maintain that sort there. Then minus, come over here, 5 times, enter this root 16 times 2. 16 is a perfect square. Root 16 is going to produce 4. Is that okay? Root 16 is 4. So the 4 will multiply this 5 out. It's going to come out of the square root sign because you have already evaluated its square root value. So that will now be multiplied by root 2 will be left. Come over here. 64 is a perfect square. Square root of 64 will give us 8. That 8 will come out to multiply the invisible 1 here. And 1 times that 8 will still give us 8. Then times root 2 will be left. That's very wonderful. Now let us work on and see the terms that are outside of the roots. Alright? The non-Surdic numbers, we are going to multiply them out. Okay? 3 times 5 will give us 15. 15 times root 2 will give us 15 root 2. And then minus, this will be 20. 5 times 5 is 20. They'll have root 2 plus 8 root 2. Now, did you take note of something that in these 3 terms we have here, their Surdic parts are the same. They are all root 2, root 2. So we can actually add or subtract these cases. So we'll move on. I'm going to use the rule of BODMAS to do the addition, okay? It's true that sometimes we tend to neglect it, but it's very important. That sometimes when we are not really ready for that, it's going to harm us. So it's better we apply that knowledge. Now, we are going to do the addition part first before we come to the subtraction. So this is going to be 15 root 5 plus 8 root 2. Let me just write it out. Let me just write it out for the case of explanation, 20 root 2. So this is how we arrange that. Is that okay? Following the rule of BODMAS. And then, oh, this is root 2. 15 root 2. I don't know what happened. I've written root 5 there. Please take note. Root 25 will produce this 5 for us. I'll be left with root 2. I'm sorry about that. That's what makes me a human. Not go mistake sometimes. Okay, but we've been able to correct it. That's the most important thing. So as you do your work, always look through. Okay? Now let's move on. We can work out this 15 plus this 8, then minus 20. That's what we're going to get. 15 plus 8 minus 20. Then we factorize the common surd, which is root 2. 15 plus 8 is 23. 23 minus 20 is 3. Then times root 2. So that gives us root 3 root 2. I guess we're done with the question. Therefore, 3 root 50 minus 5 root 32 plus root 128. Do you see that no matter how these numbers are, the final result is simply 3 root 2. And this is our answer. This is the solution to the second part of the question. In the next video, we're going to look at problems on surd rationalization. And of course, as you know, we're going to apply both the general method and the Ommakar CDRL multiplication method.